Hello, everyone. We want to start out by saying thank you for attending our presentation on power plant protection and control systems upgrades for improved reliance. My name is James Meany, representing the energy and chemical sector of our employee-owned company, Merrick & Company. Quick background about Merrick. As stated, we are employee-owned and have been since our inception in the mid-1900s. We have around 750 employees with our headquarters based out of Denver, Colorado. We are a multidiscipline engineering, architectural, and surveying firm. We serve our clients in a broad range of markets, including energy, national security, life sciences, and infrastructure. We have 24 offices with a few non-domestic offices located in the UK, Mexico, and Guam. To highlight some of our capabilities, as a full-service engineering firm, we offer an owner-engineer support that encompasses project and program management, cost estimating and decision/risk analysis, procurement, survey and asset management, construction management, and project commissioning, just to name a few. This presentation features a specific project that Merrick led from the conceptual project planning stage, Phase 1, through detailed design and on-site commissioning, or Phase 2 and 3. In addition, we will highlight a few plant asset management programs we supported for our client at the same facility. All right, let's kick things off. Our client in this case was Tennessee Valley Authority, or TVA. TVA had experienced a series of protective relay failures at their Ackerman combined cycle plant, as well as fleet-wide with the use of similar relays. The relays were nearing the end of their expected life cycle, and during the most recent PM activities, the site experienced a handful of failures. In addition to the limitations of said legacy relays, arc flash incident energies were elevated beyond the client's desired levels. Lastly, the client was looking to collect and analyze plant data to support building their asset management condition-based monitoring programs. Merrick's proposed solution, determined through a Phase 1 analysis, was to perform a balance of plant relay retrofit replacement of all 32 GE Multilin microprocessor protective relays. The relays would be replaced with Schweitzer Engineering Laboratories cell relays. The design effort started with a full electrical power system analysis using the software program ETAP. The study provided a protective device setting coordination reset and confirmed the method of integrating an arc flash reduction program with the use of maintenance mode switches. The recommendation of adding a new plant-wide protective relay network supplied a means of improving system monitoring as well as supplementing the asset management initiative. The first steps in the relay replacement were to identify the relay manufacturer, model the electrical system in ETAP, and perform a system coordination study. The graphic we are looking at here is one of the many time current curves, TCCs, that were used to analyze the system protection response, calculate the worst case arc flash incident energies, and decide the protective relay settings. To explain what we are looking at here, these curves represent the expected protective device trip curves. For the TCC, we get a visual depiction of equipment protection. In this graph, we can see that Station Service Transformer 3 is protected, and we maintain coordination as we go up the time current scales. The highlighted portion shows how the system protection is changed by enabling the maintenance mode settings, which in turn activates the instantaneous function. In this slide, we see a portion of the protection single line modeled in ETAP and the calculated arc flash incident energies on the medium voltage bus system, in this case 6.9 kV. Arc flash studies are performed using the IEEE 1584 method, and we can see the arc flash boundary is 90 feet. This is due to the fact that the protective devices take up to about 3/4 of a second to clear the fault. This indicates that if a worst case full 3-phase bolted fault were to occur, person standing within 90 feet of the gear would experience a second-degree burn as a result. The protective device settings are set in a way to maintain coordination with each other to ensure reliable operation. This is sometimes at the expense of increased incident energies. This is a scary realization, hence why arc flash mitigation programs are very important. With maintenance mode switches, you get the best of both worlds: reliable operation during normal conditions and safe conditions during maintenance activities. Maintenance mode switches enable or lower the pickup of the instantaneous overcurrent function of the protective relays, usually at the expense of coordination between devices. This slide shows the same portion of the single line with maintenance mode enabled. As we can see, there is a drastic reduction in the length of time a fault is on the system and the energy reduction gained from it. On low voltage systems, 480 volts and less, we were able to achieve lower than 8 calories per centimeter squared, which is defined as daily wear energies, meaning operators can minimize PPE requirements, making their jobs safer, easier, and more comfortable. To provide a summary of the arc flash study, prior to enabling maintenance mode switches, we see dangerously high energies and a very large arc flash boundary. When the arc flash maintenance mode is turned on, the relay trip time decreases to less than 1/10 of a second, reducing energies to just over 8 calories per centimeter squared and the boundary to 12 feet. The fault clearing time considers the number of cycles it will take the relay to detect the fault and how long it will take for the breaker to open and clear the fault. We can see a significant improvement over the system without maintenance mode enabled. We want to highlight that all calculations are theoretical, and we as design engineers can't guarantee the system will respond as the ETAP model indicates. Data is gathered from multiple sources, and the system is modeled as close to real-world conditions as possible. Although in some cases our calculations may indicate energies are reduced to daily wear values, we still highly encourage the proper use of PPE and being very cautious when working on or around energized electrical equipment. In the next few slides, we want to go over some of the steps, inputs, considerations, and etc. that went into the design aspects of the project and highlight some of the methodologies. For this project, we replaced 3 main types of relays: motor protection relays, feeder protection relays, and transformer protection relays. Each of the different relays providing different configurations, different forms of protection, and different software settings. Cell 710 motor protection relays provide overcurrent protection in the form of thermal overload protection, ANSI protection function 49, utilizing a mix of thermal data acquired through RTDs and settings derived through the nameplate rating of the motor. These relays have smart learning algorithms with the use of the RTDs to analyze thermal capacity usage and determine or learn the motor cooling time, start inhibits, and health of the motor bearings and windings. Overvoltage settings are set to prevent damage to the motors due to high transient voltages. Motors are typically designed to withstand 75% of their rated nameplate voltage for up to 60 seconds. As such, the undervoltage element, or ANSI 27, is set to trip before this can occur. Other protection functions include the neutral overcurrent, or 50G, mechanical jam, which functions as an instantaneous overcurrent, or 50, a load loss/undercurrent, ANSI device code 37, which typically indicates a mechanical failure, and a current imbalance, or 46, which provides protection for winding-to-winding short circuits. Included as well is an RTD biased trip set based on manufacturer nameplate ratings. In addition, the RTD data is monitored via the plant distributed control system via added daisy chain Modbus connections. Each MCC section has a dedicated connection to the DCS in lieu of each relay, saving on the space and installation costs. This allows the client to monitor all motor temperatures from the control room and track trends. Feeder protection relays are the most straightforward relays replaced in this project. They typically only include overcurrent protection, which are ANSI device codes 51, 50, and 50G. The time overcurrent protection, or 51, is set based on the manufacturer recommendations, IEEE 242 standard, NEC 450.3, and ETAP coordination results. In addition to the overcurrent protection, the main system feeder relays, configured in a main-tie-main scheme, support under and overvoltage protection to aid in the automatic transfer scheme. The last of the relays replaced were the generator step-up, GSU, and balance of plant unit aux transformer protection relays. Transformer relays are generally a more complicated relay with multiple functions encompassed in the protection scheme. Differential protection settings were calculated taking into consideration other systems, in this case, the generator static frequency starting system. Also, a NERC compliance evaluation was detailed as required in the PRC standard. Another feature added was the iRig-B GPS clock to support the deployment of the Phaser Monitoring Unit, or PMU, capability within the relay. One of the main challenges of this project was implementing a new transfer scheme for the main power plant distribution switchgear. In addition to the two substation transformers feeding the main setup, which is typical, the plant also had a backup feed from an external utility connected to one end of the system. To operate the buses safely, you have to have the tie open when both mains are closed, and you must have the tie closed with both mains open when feeding from the backup feeder utility. Leveraging the configurability of the microprocessor relays, we were able to utilize the communication mirrored bits function of the CEL 751 to offer a sophisticated, secure, and automatic main transfer scheme. A few features we added were time delays to the trip and close push buttons to increase operator safety, indication and alarming when maintenance mode is enabled, and a permissive bypass when choosing to operate from the backup utility feed. Traditional interlocking schemes utilize non-sophisticated under and over voltage relays and breaker position contacts to support operation, but they severely limit the flexibility of the main operation. In other cases, programmable logic controllers, or PLCs, provide a means of operating the scheme, but by utilizing the relays themselves, we cut down on costs, real estate, and eliminate another potential point of failure. One of the requested features for this project was to add the ability to record the generator's synchrophasers via the relay PMU functionality. Capturing and visualizing this data supports NERC-required response evaluation reporting, which historically is done so during generation downtime, requiring unit operation in non-normal conditions. In addition, rolling out PMU capturing fleet-wide can support a system monitoring program and provide a microgrid operation to improve grid reliability, system response methods, and future planning. In addition, rolling out PMU capturing fleet-wide can support a system monitoring program and provide a microgrid operation to improve grid reliability, system response methods, and future planning. To support the value-added PMU functionality and utilize the full ability of the new relays, a relay communication network was included in the project design. The new network provided GPS clock distribution and created the ability for remote access and further data exchange capabilities. To note, PMU functionality requires a high accuracy clock signal, one that is not available via Precision Time Protocol network distribution, hence why the PMU relays, the GSU relays, have iRig-B clock connections. The integration of the relay network provided an increase in command center operability and engineering monitoring and report tracking. With this communication network, site personnel would be able to capture event reports and perform remote relay operations from the safety of their office. Relay operation is protected by a multi-tiered password, with each tier allowing more control of the relay, with remote tripping at the highest tier of security. This allows for certain personnel to access the event reports and metering data without access to the breaker operation, whether accidentally or intentionally. Adding such networks can be relatively straightforward, and if existing fiber infrastructure is available for use, as in this case, connecting to the devices outside of the central location is easily manageable with the use of media converters or additional switches. One thing to highlight when building or adding to a network, especially when connecting with outside networks, is a cybersecurity assessment is imperative to ensure protection from the outside threats and compliance with standards like NIST, NERC CIP, and ISSP 99. The project construction was planned and completed during a routine 3-week plant outage coordinated with other plant work. Merrick and TVA enlisted the construction support of a third party, Vertiv Electrical Reliability Services, in which 4 to 6 electricians worked full-time for the duration of the outage. The work encompassed testing all of the protection voltage and current transformers, the replacement of all 32 relays, as well as the commissioning and return to plant operation procedures. The detailed design phase encompassed the compilation of a detailed testing and commissioning plan and construction sequence schedule. In summary, the project was completed on time and under budget with the help of using a stage gate front-end loading engineering method while implementing lessons learned from past relay upgrade projects. The project increased personnel safety through the creation of an arc flash reduction program, integrated a plant-wide relay network to allow remote operation and monitoring, and added other features like time delay relay plant operations for local switching. Reliability was enhanced by replacing the aging assets, creating a system model to support the protection settings coordination, and the addition of the relay-based automatic transfer scheme. One of the major highlights from this project, especially from an owner's and operations standpoint, is that it supports the ongoing asset performance and condition-based monitoring programs. Capturing of the generator's synchrophasor data with the use of the relay PMU functions provides input in the fleet system model and is utilized to balance and manage in a microgrid fashion. In addition to this project, Merrick has performed other asset performance and condition-based program projects at multiple coal, gas, and hydro power plant facilities. At Ackerman specifically, Merrick led the owner engineering efforts for 2 other projects. The first was the addition of a thermodynamic response modeling software. This project encompasses monitoring of system feedback signals to support the creation of an empirical model and monitor the cycle. It also provided a proactive root cause analysis. For example, cooling water flow, heat recovery steam generator differential pressure, and systems drains are key inputs into the model. The other project Merrick implemented at Ackerman was a data acquisition system, or DAS, to automate the collection of critical asset data. The DAS provides a high-resolution anatomization of key equipment data. In this case, boiler feed water and cooling pumps loading and vibration, generator step-up transformer thermal imaging, and turbine vibration signals were collected for analysis. In closing, it is important to Merrick as employee owners that we provide our customers a strong solution to reviving aging assets and support the enhancement of smart monitoring programs with the use of analytics. The Ackerman Relay project replaced failing assets, increased site safety, and provided the addition of a comprehensive network and monitoring program. The use of key planning and a front-end engineering methodology allowed this project to be executed during normal planned system outages. Now I'd like to answer a few FAQs before our scheduled Q&A session. Question 1. What other means of reducing arc flash energies are there aside from the maintenance mode switches? Arc-resistant switch gears are an option. They are designed in a way to direct arc flash away from the front of the gear where operations take place. As this project was a retrofit project modifying existing switch gears, this wasn't an option. With newer relays, there is always an option to include arc flash detection fiber located throughout the gear and monitored by the relays. The fiber can detect arc events before they grow and trip the breaker to clear the fault, usually faster than by detecting a fault through a CT monitoring. What is the cost benefit of a relay network? As the relays come pre-configured to connect to a network, the only setting additions to the relay is entering a predefined IP address. The only other additional costs are potentially a network switch if your installation does not currently have one, or spare ports to support all relays and the installation costs of running fiber or Cat Ethernet cable to all relays. The benefit is that there is no need to check the metering data, event reports, settings, or perform relay operations from directly in front of the switchgear where the relays are located. All of this can be performed from the safety of the control room or your office. Question 3. Why replace the relay units before failure? Assuming that spare relays are readily available in the event one fails, you still have to deal with the repercussions of a relay failure. If the relay that fails was non-critical to plant operations, any repair activities would have to be done on a live gear. If the relay that fails is critical to plant operations, then you have to handle an unscheduled outage to repair, losing on generation time and potentially costing you far more than the relay is worth. If you replace the relays during a planned outage, then the relays are likely to pay for themselves by improving reliability and reducing the chances of an unscheduled outage. Once again, from everyone at Merrick, we'd like to thank you for attending this presentation, and please feel free to ask any and all questions you have at the Q&A session.